In this video, we're going to talk about energies of reactions. So if you burn some gas on a stove to heat up some water, and you burn for like 3 seconds, your water probably isn't hot yet. You have to let it keep going. It takes a couple minutes before it's boiling. The more you burn, the hotter the water gets. So there is a certain amount of energy that is released for a certain amount of a reaction happening. Think about methane, CH4 plus 2O2 going to CO2 plus 2 water. Well, let's say I have 1 mole of methane, so 16.015 grams of CH4 is burnt. I could use that to find the moles of any of my chemicals. I would take my weight of methane. I would say, well, it's that many. I specifically chose the same amount as a mole. So it's that many grams of methane in 1 mole. So I have 1 mole of methane. I could then say, well, hey, my balance reaction is 1 mole of methane for every 1 mole of CO2. I could solve my CO2. So that would give me 1 mole of CO2. We can use stoichiometry to go from weight of 1 compound to moles of that compound. We can use the balanced reaction to go from moles of 1 chemical to moles of a second chemical in the reaction. And then, if I wanted, I could take those moles and I could use a molecular mass and I could find the grams of carbon dioxide. This is standard stoichiometry for a balanced reaction. Advantage we have here is we can go back to this component. If I want to know the energy of reaction, well, if I knew how much energy 1 mole of methane would release when it burned, I would have a ratio for it. I could plug it in and solve. These exist. They are called the delta H of reaction. So delta H is called the change in enthalpy. So the change in enthalpy is the change in heat energy. It is the heat energy change. It's basically a measure of how much heat energy was released when the potential energy was converted. It's an easy thing to measure. We just watch how hot stuff gets. And so we tend to use these to track the energies of reactions. For methane burning, it is minus 213 kcal. What that means is the atoms lose 213 kcals when they react. They used to have that in their potential. They lost it. They gave it away. Well, we can kind of think of energy, of heat, as a product of this reaction. When we burn methane, it gives off heat as one of the end results. So heat is a product. Now, a balanced reaction normally only involves the atoms because we need it to be balanced on both sides. I can't show you where the heat is in the potential over on the starting materials. So we don't normally write heat in as a product, but we can recognize that, yeah, it gets hotter when we do this reaction. It gives off heat. What's really happening is that it is plus 213 kcal of a product. Now, we said our delta H was negative 213. Well, that's because the atoms lost it. There still is physically 213 kcals, so when you write it as its own product, it's positive. But that is no longer in the atoms, so the delta H of reaction says that the atoms lost that 213. Well, there's no reason we can't treat that like part of the balanced reaction. We don't normally write it, but it is an amount that will happen, and it will be exactly that amount for every mole of methane. So in the same way that I could use the 1 CO2 and the 1 methane when I originally converted my moles of methane to moles of CO2, I'm able to do that with the energy. I can say that for every 1 mole of CH4 that I had, well, the balanced reaction says 1 mole of CH4 to 213 kcals. So let's try an amount of methane that isn't the same as a mole. In fact, let's try one of the other chemicals. I'm going to burn methane and oxygen. Let's say I burn 1.5 moles of oxygen. My goal is to find energy released. Because remember, the energy released is for the reaction. Methane itself doesn't release all the energy. Oxygen doesn't release all the energy. The collective reorganization releases the energy. So I can also find this for a certain amount of O2. I have 1.5 moles of O2 that we did burn with methane. We just added enough until it burned. The balanced reaction tells me, here are these old ones, that there is 2 moles of O2 consumed for every 213 kcals the reaction releases. So there are 2 mole of O2 for every 213 kcal. So if I successfully burn 1.5 moles of O2 with methane, well, we're going to find that that is 159.75 kcal, or basically 160 kcal. I didn't burn as much as the reaction used. Like the reaction said use 2 moles. I only successfully burned 1.5. So I had a little less than 2 moles of oxygen. I should have a little less than the energy that would come from that many moles. And that's what we find. 160 is a little less than 213. Energies of reaction, these delta H values, actually lets you calculate how much energy is released in a reaction by treating it like it's part of the balanced reaction. Similarly, if you know how much heat was released, you can find the amount of chemicals. Let's try that. In this case, let's say we released 100 kcal. So we measured the heat that came off the reaction. We realized it was 100 kilocalories that was released. What I want to know is we want to find CH4 burned. Well, I have 100 kcals of energy, and the balanced reaction, since I can treat my delta H like it's part of it, just remember that it's going to be positive, that there is 213 kcal for every 1 mole of CH4 that reacted. And so I have a little less than half the energy of the balanced reaction. I should have a little less than half the moles. 100 divided by 213, and what we find is that 0.4695 mole of CH4 must have burned. This much methane, being a little less than half what is indicated in the balanced reaction, would produce a little less than half the amount of energy from the balanced reaction. And that's what we see. So you can actually solve the energy released by a reaction or absorbed. There can be reactions that absorb energy as well. You can find it if you know the delta H of reaction. And so delta H's of reactions, and generally, unless that is what we are solving, will be provided. The idea is that we can just incorporate them into our balanced reaction. So let's try one. Photosynthesis. Photosynthesis is CO2 plus H2O goes to C6H12O6, sugar, and O2. The delta H of this reaction is positive 678 kcals. Well, in our case, if I want to make 2.7 mole of sugar, about half a kilogram. If I want to make that many moles of sugar, I want to find energy required. So remember that to photosynthesize, plants have to absorb energy in the form of light, which is another type of energy. There are more than the three we learned, more than kinetic, thermal, and potential. Those are just the most common for chemistry for us. But photonic light energy is also a form of energy. Plants harvest it, use it to reorganize bonds. Well, to make sugar required that our atoms gain energy. Our delta H reaction is positive. When the reaction is done, they have more potential than they did before. What I want to know is how much. How much energy did the plant have to absorb in order to create the sugar? So go ahead and pause here. Take a second and see if you can solve that. All right, if you're back, well, I have 2.7 mole of sugar, and my goal is to find energy, so kcals. What I need is a ratio of mole of sugar to kcals of the reaction. Well, I need to balance my reaction first then. I've got 1 carbon on the left and I've got 6 carbons on the right, so I'm probably going to need 6 CO2s. If I have a single sugar, that's going to give me 12 hydrogens on the right. I have 2 on the left, so I'm probably going to need 6 waters to get 12. That's going to get me 12 oxygen and 6 oxygen for 18 oxygen. I already have 6 here, so I need 12 more oxygen, so I must need 6 waters. So it's 6 CO2, 6 waters, 1 sugar, 6 dioxygens, and while our delta H is positive, we have to put in 678. So 678 kcal must be a reactant. It has to go in order to make the reaction happen. That still gives us our ratio, 678 to 1. So 1 mole of sugar, 678 kcals. What we'll find for that is 1,830 kcals of energy, which I guess to 2 sig figs, about 1,800 kcals. So to make that sugar, our plant had to absorb 1,800 kilocalories of energy. We can use the enthalpies of reaction in order to determine how much energy must go in or come out based on the amount of chemical, or how much chemical is required to achieve that amount of energy. We can do this by just treating energy like it's part of our balanced reaction.